name is Rishi Polapale, and this is my fifth lab for Physics 2211. So for my lab, I wanted to model the conservation of momentum. So the purpose of this lab was to, of course, model the conservation of momentum of low-speed impact and compare these experimental results that were conducted through an experiment in real life to an ideal computational model. This computational model we'll get into later, but it is, of course, under ideal conditions and is completed through GlowScript code. A quick summary of the results. The experimental model, of course, does not conserve momentum due to external forces, and we'll get into that later as well. So as far as the main physics idea, of course, we want to define momentum, which is mass times velocity. For any object, momentum can, if there is a vector, if there's a velocity vector, there is also a momentum vector pointing in the same direction, which is just scaled by the mass of the object. The conservation of momentum principle takes this a little bit further. It describes collisions. So as you can see, the mass of the first object times the velocity of the first object initially before collision, which is momentum, plus the momentum of the second object before collision equals their momentums added together after the collision. So we can see that energy is conserved and momentum is conserved there. So as far as the lab goes, we had a quick procedure. First, we wanted to record the masses of both rolls of tape. Of course, we want to use that to multiply by velocity when we want to find momentum. Then we want to launch both rolls towards each other on a smooth floor and track their movements using the tracker system. This was done by recording the rolls of tape, and we wanted to see how they collide with each other and act after the fact. We used the tracker system to track their x and y movements with respect to time, and then we created two models: the computational model with GlowScript, which was done without any experiment, and the experimental model using real tape and real conditions. So here's the system and the procedure itself. So of course the system is both rolls of tape. The surroundings are the ground, earth, the people pushing it, and any other forces such as friction or anything else. And the y-hat axis is the upwards vertical, and of course the plus axis is the rightwards horizontal. So here is the computational model code. We can see that blue tape and white tape are defined. We want to define blue tape's velocity, of course, because we need that to calculate momentum. Then we define white tape's velocity with the vector, and then we define their masses as well. Now that we have all the information we need, which are both velocities and both masses, we can calculate momentum for both of them. And then we set time equal to 0 and delta t equal to 3.33 to the times 10 to the negative second. So here is the rest of the computational model. There's a while loop, two while loops that use the position and velocity update formulas to figure out the motion of the blue tape. And on the right, we have just the finishing aspects of the model and the code. So here is the difference between both models. The top one, we can see that it says the white tape's momentum before collision was negative 0.023 and 0.04, and the blue tape's was negative 0.021 and 0.04. And then after the collision, it was the opposite, actually. So it was 0.02 and 0.043, but they were the same absolute values. Now we could tell from that there was a conservation of momentum. From that, we could tell that was the computational model. The bottom one was, of course, the observational model, because momentum was not conserved, and there was a difference in momentum for both blue and white. So the momentum, of course, is not conserved because there are external forces in the observational model, such as friction and air resistance, and the real model cannot conserve total momentum because, of course, in real life there are always external factors acting on our system. This means that the two rolls of tape are not a closed system because of the surroundings acting on them. We can improve the lab, of course, by making the system more resistant to the surroundings by using maybe a slippery surface to minimize friction, or any other types of surfaces, and minimize any surrounding effects on the system. The end. Thank you, guys.